Okay, so welcome everyone to Guided Study Group Week 8 of Math 141. So this week, as we all know, we're going to have midterm 2. And today I'm just going to have like a quick review through the materials. And then it's the solutions of some of the practice problems. So I updated these questions this morning. So it has around like 5 or 6 people did it. So it was good. Anyone who did it after 9 a.m. this morning, I didn't update it since then because it's like night in Vietnam, so I'm not gonna stay up all night and update that. So we have just kind of like some of the main things in midterm 2. So we have indeterminate forms and the Hospital rule, which is the first part of midterm 2, where we get a chance to find the limit of these 7 forms. So when we plug in the boundaries of a limit, so the limit of x as x approaching something, so when you plug in and you find it, the limit that was given is in one of these 7 forms, then you're gonna either use the Hospital rule to solve for it or put everything in the quotient form before using the Hospital rule. So the way that we did it, we've already discussed that. We can make the product difference or power into a quotient form, and then using the Hospital rule. That's pretty much all the steps that we need to do. Then we have improper integrals. Again, this is another part besides series and sequence. So improper integrals is where your integrals have a boundary related to infinity or related to a discontinuity of your function in the given interval. So we have 2 types. Type 1 is where you have the boundary related to the limit, and then type 2 is where you have the discontinuity integrand. And so there's pretty much nothing new, and these stuff we already discussed where we go through these sessions. Next part is sequence. So this starting the main materials of midterm 2. So sequence is where we talk about a bunch, like a list of numbers. It can follow the rules or it can have no rules at all. So a sequence is convergent if you take the limit of n approaching infinity and that limit exists, and it's divergent if the limit is dne or plus or minus infinity. So whoever just joined us, the new person, please put your PSU email in the chat room. Thank you. So we also have monotonic sequence where you have a sequence either increasing or decreasing, and we have bounded sequence. So it's the maximum value of that sequence is always smaller than or equal to some value, and is bigger than or equal to some other value if you say it's bounded below. Give me a second. Okay. So we also have the squeeze theorem. So this is where if you can put your sequence in between 2 other sequences which had the same limit of n approaching infinity, BL, then you have limit of n approaching infinity of Pn is also equal to L. And we also have this theorem, which is like a minor one, but it's helpful sometimes. Limit of n approaching infinity of the absolute value of an is equal to 0. Then you have limit of n approaching infinity of an is also 0. And then every bounded monotonic sequence is convergent. So if it actually, there's another way that we can prove that a sequence is convergent. If you can prove that it is bounded, both above and below, and then it's a monotonic sequence. It has to be only increasing or only decreasing to be a monotonic sequence. Then we have series where we have like a bunch of tests of divergence, integral test, alternating series test, the comparison test, ratio and root test to, kind of figuring out if a series is convergent or divergent. And so that's pretty much all I have for the review part. I wouldn't repeat whatever Dr. Casher already did and Dr. Bang already did because they run a very long review looking at their slides, and I feel like it's really detailed if you're just looking at their slide. And so this review should just dedicate it to solving some of the questions that I saw a bunch of people getting it wrong in the exam. And so the first one is the first questions in your practice exam. Evaluate limit of n x approaching 0 of x cosine x divided by e to the x minus 1. Now, if you plug in 0, you're going to see the form of this 1 is 0 over 0. So this is an indeterminate form. So you're going to use L'Hopital rule for both the numerator and denominator. So when I draw h is L'Hopital rule, and so we're gonna take limit of x approaching 0. Take derivative of the numerator. You're gonna have cosine x plus x multiply negative sine x divided by e to the x, which is now we're gonna plug in x approaching 0 again. And so this is the thing that I want to talk about in indeterminate form and L'Hopital rule, is that you have to check for if the next expression, so after we get here, is it still eligible if you want to use L'Hopital rule by plugging in the numbers. And so if you plug in x equals 0, you're gonna have 1 minus 0, which is just 0, divided by 1 again, which is going to give us 1. Therefore, this limit is going to equal 1. And so you don't have any further L'Hopital rule. Is there any question here so far? I don't know. This is pretty simple. So I guess whoever made this mistake might have forgotten the fact that to check their L'Hopital rule. Now let's go to the next questions. Evaluate limit of x approaching 0 of 1 plus 2x squared to the power of 2 over x squared. So you have this one. When you plug in x approaching 0, you're going to have 1 to the infinity. So you're going to have then limit of x approaching 0, 1 plus 2x squared, 2 over x squared. Here we're going to have this one we're going to rewrite as e to the limit x approaching 0, 2 over x squared, ln of 1 plus 2x squared. Now we're just going to find the limit of the power. So you have limit of x approaching 0 to ln of 1 plus 2x squared divided by x squared. And now we're just going to take the L'Hopital rule. Because here, when you plug in 0, you're going to have 0 over 0 for this expression. So you take the L'Hopital rule. And then what you end up having is that the derivative of the numerator is 4x divided by 1 plus 2x squared. In the denominator is going to be 2x. So this limit now is equal to 4x. Oh, 4x. U divided by 2x is going to be 2. Multiplied by 2 is 4. 1 plus 2x squared, which is going to give us 4 in this case. And so plug it back in, you have e to the 4. Is there any questions with this one so far of what we have? Okay, we're all good. Let's go to the next one. Now, it's just very similar to the previous one, so I'm gonna go through it quickly. This one we have 0 to the infinity. So let's check the indeterminate form, because I have a feeling that this is not one of them. Yes, so it's 0 to the infinity. So when you plug in, you're gonna have 0 to the infinity, and so this one had the answer be 0 because it doesn't fall into any indeterminate form. And just think about when you have 0 to any kind of power, you're gonna have it still equal to 0 regardless. Like here, it doesn't have any form be 0 to the infinity. You have infinity to the 0. So in this case, our answer is just simply 0. So we don't even need to use the L'Hopital rule at all. That's why I tell you guys that you always have to check these expression. Now let's go to the next one. It's question 4. So this is an improper integrals, and if you look at the denominator of this fraction, there is a discontinuity at x equals -1. So we're gonna draw this one as 1 over x plus 1 dx, and we're trying to see if it's going to be convergent by evaluate the two smaller integrals. So you have limit of t approaching -1 to the -2 to t 1 over x plus 1 dx, and then limit of t approaching -1 plus from t to 1 over x plus 1 dx. Now let's check all of them individually. So you have limit of t approaching -1 to the -2 to t 1 over x plus 1 dx. This one is limit of ln of x plus 1, and it's going from t to -2, which is going to give us limit of t approaching -1 negative ln of t plus 1 minus ln of -2 plus 1, which is going to be absolute value of -1, which is ln of 1, which is 0, to minus 0. Now you look at the thing here, as t approaching negative to the -1 to the negative, t plus 1 is going to approach 0 minus. And if you take the absolute value of that, it's still going to be 0 plus. And ln of 0 plus is going to be -infinity. And so one of the complementary integral is already divergent. So our conclusion is that the entire thing also diverges. Is there any questions so far with what I did here? Okay, if we don't, let's go to question 8. Determine the convergence of this series. So it's a series from n equal 1 to infinity of ln n plus 1 over n minus ln of n plus 2 over n plus 1. And so looking at this, this is one of the way to represent telescoping series, because the ln of a quotient can be represented as a difference. So we're gonna have this series. If you this one can be written as ln of n plus 1 minus ln of n minus ln of n plus 2 plus minus of minus is a plus. So you're gonna have ln of n plus 1. And so in this case, what we end up having is that, wait, is it actually in the telescoping series? Oh shoot, no, not really. This is not the way that we should write it. Yeah, hang on. Give me a moment. So you have a difference here. And so you have a kind of like a property saying ln of a minus ln of b is going to be ln of a over b. And here we have that one is going to equal ln of n plus 1 over n multiply n plus 1 over n plus 2. This one is like a pretty weird one. And so this one is going to give us ln of n plus 1 squared and multiply n plus 2. And so it is going to give us, now let's write down the terms that we see it. This is going to be ln of 2 squared, which is going to be 4 over, pretty odd. When I look at this one, the first thing that comes to my mind is this is the telescoping series. But now as I write down, it's pretty weird about whatever is the form. So, as we're working on this together, anyone have any idea of how to do this one? Because I don't even remember what is the answer for this. So let's skip. That is true. Alright, let's write down the terms that you said it is. I thought there's like a way to make it easier, but yeah, I guess I just make it harder in my way. So let's do it this way. Yeah, I'm not really fully awake right now. It's like 5 a.m. in Vietnam. It's pretty annoying. Okay, so let's plug in n equal to 1 to 2, 3, 4, 5. We don't need to go to 5, but let's do when n equal to 1 is ln of 2 minus ln of 3 over 2. Then we have ln of 3 over 2 minus ln of 4 over 3. ln of 4 over 3 minus ln of 5 over 4. And then when n equal to 4, it's ln of 5 over 4 minus ln of 6 over 5. Now, in this case, you can see that these terms clearly cancel out. And so, therefore, we're going to have the entire sum. If you go to n, you're going to have ln of n plus 1 over n minus ln of n plus 2 over n plus 1. And so this term is going to cancel out with like a term of negative ln of n plus 1 over n previous to that. As you can see here, this term is going to cancel out with the term previous to this. Therefore, our series is going to be equal to ln of 2, which is the only term that's left here, and this term minus ln of n plus 2 over n plus 1. Now, as n going to infinity, this entire term is going to be ln of 1 because n plus 2 over n plus 1 is going to approaching 1. And then this one is going to be 0. Sorry, 0, not 1. Okay. ln of 1 is 0. And so the entire series is the n partial sum of the series is going to equal ln of 2. And so this one is convergent. Is there any questions so far with what we did here? Isn't that ln of 4 over 3? Why is it ln of 4 over 3? Okay, let's go to the next questions. Okay. Determine the convergence of this series. And so I think this is like geometric series, and I was surprised that someone did something wrong. So obviously we have to be careful here, because since whenever it comes to geometric series, the only mistake that I can think of that people might make is the algebra. And so let's go through this together. So you have a series from n equal to 1 to infinity, 2 to the 2n plus 1 over 6 to the n. And so this one here is going to equal 2 to the 2n multiplied by 2 divided by 6 to the n. And this one is going to give us 2 multiply 4 over 6, because it's 4 to the n here. So it's 2 over 3 to the n, because 2 to the 2n is 4 to the n. And then 4 over 6 is 2 over 3. Therefore, we have a geometric series with r equal to 2/3 and a, which is the first term in the series. And as I say, you find this by plugging in the first value of n into this and find what is the number of this entire thing. So 2 multiply 2 over 3, because that when n equal to 1. So you have 2 multiply 2 over 3, which is 4 over 3. And so this one, since r is smaller than 1, this is a convergence series by geometric series. And here it's only asking you to find what is the convergence of the series. So you don't need to find the sum. But if you want to, that's fine. You just need to know that it's a convergence series, because the factor is 2/3, which is smaller than 1. So we'll say, is there any questions so far? Yeah, it's going to be 4 over 3. 1 minus 2 over 3, which is going to give us 4. Yeah, that's right. The sum is equal to 4. Let's go to the next questions if no one is struggling here. So question 11. This is one of the questions that have the most people got it wrong. So it's saying, suppose that every term of this series, an, from n equal to 1 to infinity, are positive, and the series is convergent. Suppose also that every term of the sequence Bn from n equal 1 to infinity satisfying this. So Bn is always smaller than An for every terms. Which of the following statement must be true? So let's look at them individually. So first one, limit of n approaching infinity of ln Bn plus 1 over 2 is equal to half. Now, when you have, first of all, you have 0 is smaller than or equal to Bn, bigger than, smaller than or equal to, smaller than or equal to An. And so, and then we have the series of An is, every term is positive and also convergent. Therefore, we have the series of Bn from 0 to, from infinity, n equal 1 to infinity is also convergent by direct comparison test. And so when you have a convergent series, you have limit of n approaching infinity of Bn is 0. So that is why this is the only thing that really matters in this questions, because we need to know what is the limit of n approaching infinity of Bn to solve that. And to solve that, then we have ln of 1 over 2, which is going to give us 0 over 2. So this one should be equal to 0. And so this one is false. Before I go to the next questions, is this to like the next statement? Any questions so far? Okay. So the second one, we already did it, is convergent by direct comparison test. So this is correct. And then number 3, we have the sum of the series of An plus Bn. Now both of them are convergent. AN is convergent and BN, we just proved that it's also convergent. So the entire sum of two convergent series is also convergent. So this is the sum of AN plus the sum of BN, because each of them is individually convergent. So this one is also correct. So the answer is that only 2 and 3 are true. So is there any question with this question? Because I saw at least 3 people that already did the exam get this one wrong. So not the exam, did the practice exam, get this one wrong. So I just want to mention this in today's review. Now, if not, let's go to the next one. So this one is kind of similar, and again, has a lot of people got it wrong. Suppose that every term of this series AN are positive and the series convergent. Which of the following series are also convergent? Now, let's look at the first one. We are given that series of AN is convergent. So here, the only thing that we can do is maybe try to compare it with AN. So we have AN over 2 to the n. It's always bigger than 0 because it's positive and you divide it by a positive number, which is 2 to the n. And it's always smaller than or equal to AN if you're starting from n equal to 1. Why? Because the term is going to be AN, so it's going to be A1 over 2. A2 over 4. So every term is smaller than AN. And so the entire series is also smaller than AN. And so in this case, we have this one is convergent. So the series over 2 to the n is convergent by direct comparison test. And so this one is convergent. Now let's looking at the next one. When you have a limit of, this one is convergent, right? And so you have limit of n approaching infinity of AN is equal to 0. That is the property of a convergent series. However, if you look at the term here, since we have limit of n approaching infinity of AN is 0, the limit of n approaching infinity of AN plus 2 is equal to 2 and different from 0. So this series is divergent by test of divergence. Now, lastly, this is the one that I observed that people got wrong the most for this question because they have no idea if it's convergent or not. So this one too. So you can do this questions by maybe putting one of the using one of the examples. So say if you have AN is 1 over 2 to the n. How do I know that I'm going to use this kind of questions to use this kind of series? Well, when you look about it, it has the nth root. So you can give one of the convergent series positive and also have the n power. So it's going to cancel out with the n root, and it's like one of the simple example you try to put. Now, if you use it at either half to the n or 2/3 to the n, both of them are convergent by trigonometric series, so there's no problem. And now you take the limit of n approaching infinity of this, it's going to give you either half or 2/3. And all of them are different from 0, so you say, is this divergent by test of divergence? Now, a lot of people, when they take this part, and they kind of like mistake it to be root test, and they say it's smaller than 0, and say it's absolutely convergent. Well, that is not right, because the root test only apply when you're given this series, AN, and then you find limit of n approaching infinity of the n root of AN. Now, the series given is the n root, And basically by finding it, so instead of writing the nth root of an, if you write as bn, so this is basically finding the limit of n approaching infinity of bn, and this is not the n root of bn of the given series. Therefore, this is not root test, just to make sure the people and make this thing clear. So before I go to the next questions, is there any problem so far? Okay. Why the, okay, as I say, you can give any series. So okay, the way that I make out of this is that to claim that this sentence is true, you have to point out that it's applicable to all the convergent series and positive. However, if you can point out one of the positive and convergent series that make this statement wrong, then you can say that the statement is wrong. That's why I try to give one of the example to that's satisfying your conditions but make this statement wrong. So here you see the nth root, right? So the first thing that comes to my mind is that, okay, we should have some positive and convergent series but have the nth power, because it should cancel out this nth root here. Therefore, I was thinking about the trigonometric series. And so to give like a positive trigonometric series, why not have to? Okay, just think about it. So when you have something an to, okay, let's change it to another color. If you have an to the 1 over n, right? So this one is another way to write it. And then if you continue to give 1 over n and the entire thing to 1 over n, is it gonna make your problems harder or easier? Because here you're gonna have 1 over n plus 1 over n is 2 over n. Is it helpful to you? Because when I have this series, I have no idea how to solve it, right? So the point of we giving it to the n and to and also if you have this series, do you know if it's convergent or divergent? If you give it to the n, that is the form of a trigonometric series. That's why we already know that it's convergent and it's satisfying your conditions given in the problem. Here it asks the series an to be positive and that convergent, right? So if you want to give an example that counter this argument, then you should give a positive and convergent series. So that's the first thing that comes into my mind, especially when you see the nth root, right? If you want to cancel out that nth root, you have to give a series to the n, and so when the entire thing to the n root, which is to the power of 1 over n, then it cancels out and it makes our life easier. Do you see what I'm saying? Okay, cool. Now we got ready for the next one. So I'll get a break for me. I need some water. So if anyone wants to do this one, please feel free to do that. And we'll be back in a minute. So anyone have any ideas of how to do this one? Please type what you think that we should do for this series into the chat room. You can use ratio test. That's one idea. Is there any other one? Let's look at the series and some of the traits that it's going to give you. So if you use, yes, it's new root test. Why? Because you have an n here. Someone might concern about the numerator when you have -1 to the n minus 1. But when you take the root test, you take the absolute value of the root test, so of the series. So you have not of the series, but of the n term of the sequence. ln of n to the n. So when you take limit of n approaching infinity, the nth root of an, this one is limit of n approaching infinity, 1 over ln of n to the n. And so this one is going to be 1 over infinity to the infinity. Infinity to the infinity, it's just going to be infinity. So 1 over infinity is just going to be 0. And this one is smaller than 1. So this is absolutely convergent by root test. So is there any questions so far with this one? I think one of the reason that whoever get this one wrong is that because he or she might use ratio test, and it's gonna give, I think in this case it's gonna give us something that we have no clue, or it's really hard to find because if you do the math, it's gonna be ln of n plus 1 to the n plus 1 over ln to the, or ln to the n, or ln of n to the n divided by ln of n plus 1 to the n plus 1. And so, I mean, I know how to define that, but I don't think you guys have any clue of how to find it because it requires a lot of algebra to do, and it's going to make your problem really, really long. And so this is not a wise choice to use ratio test, especially in this case where you see the n power. How is n root of an is equal to an? No, an here is negative 1 to the n minus 1 over ln of n to the n. So when you take the absolute value of an, so this part it's just going to be 1, right? Because it's going to fluctuate between negative 1 and 1. But if you take the absolute value, it's just going to be 1. So absolute value of an is 1. And then this part is always positive, ln of n to the n. So you have from here to here. Yeah, you still have the n. Oh, sorry, shouldn't have included. Sorry. Yeah. You don't have. Okay. Sorry. Yeah, copy it down wrong. But then sure, you have ln of n. So thank you for pointing that out. So it's 1 over ln of n, right? Okay, sure. Let's go to. Yes, n going to infinity, so it's 1 over 0. Yep. I mean, it's essentially still going to 0, but you're right. Like, that's just a very important mistake because if there's an n, sometimes it's going to change the entire problem. So, yep. Let's go to the next questions. We have, what is this one actually? I think I have another one after this, which is sweet. But anyway, okay, this is the last one. It's question 25. Determine if this one is absolutely convergence, conditionally convergence, or divergence. Now, I would say this one related to one of the problems that we already did in, I think, when we talk about one of the sessions in the test. So say when we talk about one of the, I remember this one is in integral test, where I asked you guys, what is the value of p ln of n to, I don't remember if it's this form, or is it 1 over n ln of n to the p? What value of p that makes this convergent? And so in this case, if you use the ratio or the root test here, it's basically going to give you 1. And so it's not really leading you, wait, hang on. It's going to give us, which is 1 multiplied 0. No, not really. It's ln of n plus 1 divided by, no, it's going to give you 1. And so ratio and root test, because here, if you think about it, when you have this one, and then the n plus 1 term is going to be just 1 over n plus 1 multiply ln of n plus 1. As n going to infinity, those two are kind of like going at the same rate to one another. So let's try that and show you like ratio test wouldn't really work. So you have limit of n approaching infinity, a of n plus 1 divided by an, and take the absolute value. This one is going to be limit of n approaching infinity, ln of n multiply ln of n divided by n plus 1 multiply ln of n plus 1. And so in this case, let's break it down into two fractions and you're going to see what I was saying here. So at n is going to infinity. This one is approaching 1. Excuse me. And the next part is ln of n divided by ln of n plus 1. And this part is also approaching 1 because if you plug it in, you're going to have infinity over infinity. And if you try to use L'Hopital rule for this, you're going to find that this one is also approaching 1. And so the entire thing is just going to be 1, which make the ratio test inconclusive. And so next thing that we're going to try to use is other tests like comparison tests or alternating series tests or, maybe integral tests. And so in this case, as the first thing that I mentioned in integral tests, and usually when it comes to like a polynomial and log, that's when you're going to think about integral tests, because we know how to take integration by parts where we have two functions, and so that is the thing that's going to be applicable when you have a series with composed of two different functions. So here is n and ln of n. So you have a polynomial and a log. So that is one of the signs I show you that you should use, maybe try integral test. So if you look at the integral from 1 to infinity, 1 over n ln of n, I would try change this one to 2, because at 1 is not really defined, where you have ln of 1 is equal to 0. But it doesn't really matter if you have 1 or 2, because, well, actually it should be 2, because ln of 1 is not defined. So we have 1 over ln of n, and so dn. And so to use integral test, let's go back to that table that we have to review to see what is the conditions that we need to use for integral test. So we need the function to be positive, continuous, and decreasing. So continuous and decreasing. So here, if you look at the function, so we should actually start free to make this one positive, but it doesn't really matter of like the starting point. If you look at all of the terms in this series, except for n equal 1 and n equal 2, all of the terms starting from n equal 3 is going to be positive. If you look at this series, actually, this part, 1 over n ln of 3. And so all of the term is going to be positive. Now, is it decreasing? So I would say some of you might be questioning me right now, like, why am I doing this series when the question is giving me -1 to the n? Now, if you think about it, -1 to the n over n ln of n, this series is already convergent by the alternating series test. So I kind of like skip one step in between and jumped ahead, so bear with me on that. Because I haven't really done it on my own. I just copy it down and have a general idea of how to do it. So again, I would repeat it. So to see if this, we cannot use ratio or root test because it's give us 1 and it's inconclusive. But we're gonna use first identify to see if it's convergent or not. So we look at this series. Yes, it is integral test, but look at this one first. Is it an alternating series? And so if you use the alternating series test, you're going to see that this series is convergent. However, to see if it's absolutely convergent or conditionally convergent, you have to determine the convergence of the absolute series, which is just 1 over n ln of n. So the absolute of this is 1 over n ln of n. And so to use the integral test, as we all know, is that we have to check if it satisfies all the conditions. So it has the conditions that this thing inside 1 over n ln of n has to be positive, decreasing, and one other thing is, I think the last conditions as we see it is, it has to be bigger than 0, continuous, and decreasing. And so if we look at here, all of the terms, let me move. So all the terms here is positive starting from n equal to 3. So except for n equal to 1 where the entire thing is not defined. Where the entire thing is not defined and n equal to 2 where it's negative. Every other term of the series is positive. So it's satisfying generally if you start an integral from 3. Then you have the decreasing. So you look at the denominator here. The numerator is always 1, so it's always constant. But the denominator is always increasing as you increase n. Therefore, it's a decreasing series because as the denominator increase, the entire fraction decrease. So it's a decreasing series. And we also have it's continuous because starting from n equal to 2, all the value of ln is defined. So all the value of ln is different from 0. So n equal to 1, ln of 1 is 0. And so it makes the entire fraction is not defined. But starting from n equal to 2, ln of 2 is not 0. So the entire fraction is defined as continuous. Now, when we use the integral test, we have to identify what is this integral. And if it's convergent, then your series is also convergent. And so to find this one, we're going to use u sub. So we have if you substitute u as ln of n, then you have du is going to be 1 over n dn. And so I will have this one is going to equal, the entire series is going to equal ln of 3 to infinity. Or you can actually not, we have to take that infinity away. T approaching infinity, t ln of 3, and then you're going to have 1 over u du, which is going to give us ln of u, limit of t approaching infinity, of t to ln of 3. And obviously, when you plug in ln of t, which is ln of infinity, this one is infinity. So it is divergent. And so the absolute series 1 over 2, 1 over n ln of n is divergent. But then you have by alternating series test, -1 to the n of n ln of n is convergent by alternating series. Therefore, you have this one is conditionally convergent. So, is there any questions with what I did here? If I'm going, could you do an arrow example? Give me a second. I need to pull it up from the exam. And so let me stop the recording for a moment and I'll do so resume the recording. And so, okay, let's see what we have here. So we have, if we use this partial sum to approximate the sum, like S4, then according to the alternating series estimation theorem, the magnitude of the error. Alright, so based on the alternating series estimation theorem, sorry, not there yet, the error Rn is more than or equal to Bn plus 1, which Bn is the series, not Bn, but -1 to the n minus something. Bn is like the positive part of the alternating series. And so here you have the error is smaller than or equal to 1 over n plus 1 squared, which is the positive part, which is Bn. And now here, when we use S4, so n here is equal to 4. And so this one is equal to 1 over 5 squared, which is going to give us 1 over 25. So that one is one of the way that they can ask you about error in the exam when you use alternating series estimation theorem. Is that what you're looking for, Kyrie? Or if you want me to do and look for other example in the exam, I would do that. Yep, this is kind of like the basic thing we're going to be asked. And I also did this example when I do alternating series test. So if you need more review, please feel free to go back to that sessions, that recordings. So is there any final questions that you guys want to ask, or like, is there any problems in the exam that you want me to go over, in the practice exam that you want me to go over and I didn't? Please raise it up now, because after that I'll end the sessions and I can only wish you luck in the exam. Okay. So I'll take it as there's no questions. So good luck on your exam. And so I'll see you guys next week, where we're gonna start think about our final exam. But first, survive this one first. Let's see. Yep, no problem. I'll see you guys next week. Yep. Have a great weekend and good luck on your exam, guys.